Thank you for everyone to watch this video. So the title of this work is Leopard, Understanding the Threat of the Blockchain Domain Name-Based Malware. It's worked on with Zhangrong Huang and Tianning Zang. So we are here to talk about a new technique used by malware. Let me shortly introduce existing techniques which are widely adopted by malware. IP flux is a technique which enables malware to change IP addresses of their CC servers quickly. The right diagram is a simple version of the mechanism. It's a DNS technique used by botnets to hide malicious sites behind an ever-changing network of compromised hosts acting as proxies. Another technique is domain flux, and the main point is the domain generation algorithm, also called DGA. Bots and CC server run the same algorithm and generate a bunch of domains, but only a few of them are available for bots to access the server. What is blockchain domain name-based malware? We call it BDN-based malware for convenience. And it's a malware which leverages blockchain DNS to resolve blockchain domains. So authors added .bit domain support to malware, which is a kind of blockchain domain. Here is a sample of underground advertisement. Now, more than 140,000 domains have been registered in both Namecoin and Emercoin, which are cryptocurrency companies. Namecoin and Emercoin based on the blockchain, and all the domains are public available using blockchain explorers. But I think there are much more domains because OpenNIC is different and not based on blockchain. It's a hybrid approach in which a set of peers manage namespace registers, yet the name resolution tasks is fully decentralized. So, domains registered on their platform are not publicly available. There are some related works about decentralized DNS and the security problem of introducing blockchain DNS, but few works related to detecting malicious BDN-based malware. Approaches like Fancy and BotMiner are relatively similar to our work, detecting malware based on traffic analysis. However, they are not suitable for BDN-based malware, since the behaviors of traffic are quite different. So we need a solution to mitigate the new threat. We design a prototype system named Leopard, and it has a great performance on real-world datasets. Also, we present two datasets. One is a set of malicious blockchain domains, and the other is a list of blockchain DNS servers. Then I prepare to introduce the details of our work. I divided this talk into 5 sections. First, I will introduce some background knowledge of blockchain domains and blockchain DNS. The design of Leopard will be presented in detail and evaluate the system with a real-world dataset. At last, we discuss the limitation and conclude the whole work. Let's begin with background. Blockchain domains have particular TLDs, which are different from generic TLDs and country code TLDs. The right table is an example of TLDs of blockchain domains. Besides, blockchain domains have some significantly attribution for attacker. They are anonymous and censorship resistant. You can see it in the right figure. The owner of Alibaba.Buzzer is only a hash string. For ordinary domains we daily use, you can get a lot of information about the owners of the domain using who is the service. So it's hard to track blockchain domains. How to resolve a blockchain domain? The left diagram is the resolution procedures of ordinary domains, which we are familiar with. Blockchain DNS is like a peer-to-peer network, and the DNS records on each server are the same based on distributed ledger technique. User can issue a blockchain domain query to any server. Here are two different ways to resolve blockchain domains. One is third-party BDNs. The device sends domain resolution requests to tools like proxies or browser plugins, and they will forward requests to the right servers, which provide blockchain domain resolution service. It's also the same as mentioned in the previous slide. The other is local BDNs. If users set up a blockchain resolution service in local device, they can look up local blockchain for DNS record. Then we step into the automatic detection. Here is the overview of Leopard. The system consists of three modules: data collection modules, data process modules, and discovery modules. The system collected DNS traffic from an ISP and transformed it into DNS logs. Then logs will be filtered and aggregated according to a design format. Supplementing missing value is necessary before extracting features, and followed by a standard training test workflow. In the data collection phase, we collected 400 samples of BDN-based malware and ran them in Cloud Sandbox to get captured traffic files. We extracted 169 malicious blockchain domains and used Dig, a DNS lookup tool, to find out all named servers queried by malware. We used NSList to filter DNS traffic of the active malware. In data processing module, the system leveraged AlexList to filter the collected DNS logs. After that, the raw data are split into ordinary domain data and blockchain domain data. ODN here stands for ordinary domain names with generic TLDs or country code TLDs. Then Leopard aggregate both of them. For blockchain domains, we had to label them using VirusTotal and checked whether domains are in the blacklist or blocked by servers. The blacklist consists of domains we collected from 400 malware samples, and the servers responded to particular IPs for blocked domains. For labeled blockchain domains, the system supplemented missing values like DNS records of domains using blockchain explorers. Here is a screenshot of the explorers of Emercoin. The Explorer is a web application to show data of blocks. Finally, we got our dataset. Feature engineering is applied to the dataset. The dataset will be split into three parts: training set, test set, and unknown set. The unknown set consists of all the records without labels due to existing NX domains responses or domains not being detected by VirusTotal. We trained 4 types of classifiers: L2 logistic regression, linear SVM, random forest, and neural network. We picked the best one as the classifier of our system. Before evaluating on unknown set, the classifier was retrained on the whole dataset. Next, we evaluate Leopard with real-world traffic. In the evaluation phase, here are 2 goals of our system. We want to know if Leopard does have ability to detect malicious blockchain domains and discover unknown blockchain domains. First, let's see the dataset. With the assistance of the ISP, we collected 90 DNS traffic, about 59 gigabytes of raw data, and observed a total of 13,035 IPs. To compress the data storage and conveniently extract features, we designed an aggregation format. At the first line, request IP is the server IP which is queried by client, and at the second line, IPs in source list are client IP addresses. At the third line, each DNS record of the domain and the corresponding TTL will be packed as the tuple. The format can provide a view of servers to observe the client behaviors of each domain. We merged the data of the first day to the 6th day into the training set, and merged the remaining 3 days into the test set. The unknown set only has records of unknown blockchain domains. We selected 17 features and divided them into 3 feature sets named time sequence, source IP, and resource records respectively. Time sequence includes the features of the time differences between packets and the number of packets per minute. The source IP includes the distribution of user IPs. The features like the number of DNS records and the corresponding TTL values are in the resource records. 4 classifiers are implemented by Scikit Learning Library. The matrix used to evaluate the performance is AUC. We trained and evaluated classifier use 5-fold cross-validation. In this figure, it's obvious that the random forest classifier is best, reaching an AUC of 0.99, and the linear modules seem not suitable to this problem. We use 2 methods to analyze features. First, we calculate the mean decrease in purity of each feature, which also is a measure within the random forest algorithm. The features of resource records play an important role in classification because they account for 6 in the top 7. Then, the different combination of feature sets were assessed by training the same classifier with different features and check their performance on the training set. We also noticed that the resource record set is essential. Next, the trained random forest classifier was applied to the test set and achieved an AUC of 0.99. When the system gets a higher detection rate and the false positive rate is a low value. So according to the result, we could say Leopard can accurately detecting malicious blockchain domains. Before applying the classifier to the unknown set, we retrain classifier on the whole dataset. At last, Leopard detected 286 unique blockchain domains and 23 server IPs. Without precise information to label these domains, we made some rules to verify the result. Step 1. We checked the historical IPs of the domain using Blockchain Explorers. Step 2. Checked client IPs of the domain using VirusTotal. Step 3. Searched threat intelligence related to the domain by search engines. If the domain matches any of them, we consider it as the malicious. According to 3 rules, we confirmed all blockchain domains are malicious, so the system also achieved the second goal. After analyzing the result of the unknown set, we found that 271 blockchain domains from this IP are different. They look like randomly generated and meaningless. Table 7 is a comparison between 2 kinds of domains. Leveraging DigiArchive website, we confirmed the hypothesis that cybercriminals try to combine the domain generation algorithm and the blockchain domain technique. Now I'm going to discuss some limitations of our work. The system relies on feature engineering and expert knowledge, which makes the system easily passed by and unstable for long-time operation. Also, you can see that we design a module to process raw data, which is time-consuming, and the system only deals with BDN-based malware. In the evaluation phase, we select the top 5,000 domains of Alex to filter ordinary domains as our benign samples. So it's a little bit biased. We should collect some DNS traffic of benign website hosted by blockchain domains, but it's quite difficult. Then let's conclude the whole work. We try to alert researchers to pay attention to malware based on the blockchain platform, and propose an automatic solution to mitigate the new threat. Also getting an insight into reported blockchain domains, and notice that attackers have already combined DGA and BDN techniques. Last but not least, 2 datasets are presented, which are related to BDN-based malware. Thank you for watching this video, and please feel free to access dataset.